And today's topic is oxidation 4. In oxidation 4, I'll be dealing it with the osmium tetroxide. So moving to osmium tetroxide, and so here this osmium tetroxide is a reagent. Specially it is used for the hydroxylation of the carbon carbon double bond. Okay, so what we are doing is we are taking an alkane and we are doing the hydroxylation. That is, when we'll take an alkane, it will result in the diol formation. Okay, so moving on to preparation, and in the preparation what happens here, the osmium, when an osmium is treated with an in presence of an air or an oxygen upon red hot. Okay, so osmium tetroxide is prepared or obtained, and in this purpose, for the oxidation purpose, the solution of the osmium tetroxide in ether or the tertiary butyl alcohol is added to the solution of an olefin. Okay, that is, you are taking an alkene, and then if you will take an alkene and in the presence of an ether, the osmium tetroxide is added. In the presence of an in ether, osmium tetroxide is added, or in tertiary butyl alcohol in the presence of base. Okay, resulting in the formation of your respective product. So I'll be dealing with this. You just go through this point. So I will explain you this reaction. The same thing will be there in this points. Okay, so we are taking an olefin. Olefin is nothing but an alkene. When an alkene is treated with the osmium tetroxide in presence of pyridine as the base, first intermediate which is formed is your osmic ester. Osmic ester is formed. Here what happens, this bond, alkene bond, will go and bind to the oxygen atom. This will shift, and then this again goes and attack to the carbon. So what happens here is there is a formation of an osmic ester, and later when if it is treated with the reducing agent such as Na2CO3, which will prevent your further oxidation oxidation products will be prevented by this reducing agent. So when we add the alcoholic Na2CO3, sodium carbonate, at that time this bond breaks by the formation of your diol formation. Okay, cis diols are formed with the regeneration of your osmium tetroxide. First, the osmium tetroxide is released, and when it is treated with an aqueous solution, that is water, that time it will result in osmic acid. Okay, so here, unlike the KMnO, for which we have dealt with the manganese reagent, so like that, similarly itself the osmium tetroxide will also act as an oxidizing agent. So here also this cycloaddition takes place with the olefin in the less hindered side of this less hindered side to yield the cis 1,2 diol as your product. So moving on to here I will show you some of the uses. Like first, if we will synthesize the osmium. Okay, so how it will look in the test tube, how it will look in RB flask. When we'll synthesize it, it is have this metal appearance. Okay, so we can use this to the pinpoint pens. Okay, ink pen, and for this, which you will see the lid, right, for making of this also osmium is used. And here for the jewelry purpose. Okay, this is a ring, this is a bangle. So jewelry is also the osmium is used, and osmium car you can see, osmium watch you can see. Here you can see the watches. Same thing, like many of the uses are there. You can just go through it. And then moving on to next slide. So now in the whatever the big previous slide we have seen is the reality show. Okay, so this, if you will see this, you have to imagine things, okay, which you will do in the lab. All right, so moving on to preparation uses. In the uses we are having certain preparations, like we'll be dealing with the preparation first. In the preparation, alkene, we are taking an alkene or an olefin. Olefin is treated with the osmium tetroxide. When this olefin is treated, at that time what happens, the diols is formed with the release of the osmic acid. And again here, if you will see, if we are taking the cyclopentaene, in at that time what happens, upon treatment with the osmium tetroxide in the presence of an aqueous alcoholic Na2CO3. Okay, so in that also the diols are formed. sorry. So here it is an indication of the orthofusion in the third ring. So you can see here, this is the third ring. There is a orthofusion reaction which is taking place. Yes, or else it is in case of an anthracene, it is an orthofusion reaction, and also you can tell it as a linear fusion of the three rings. Okay. So in same treatment will take place, same orthofusion with the two rings, that is your naphthalene also. Okay. So instead of taking three rings, you are taking only two for anthracene, and you will be ending up with the dicarboxylic acids again. So moving on to hydroxylation of an alkene. In this what happens, the exact mechanism of osmium tetroxide and oxidation is contentious. That means there is other two thoughts in which we can be dealt with 3+2 cycloaddition and 2+2 cycloaddition reaction that can also liberate with the diols formation. Okay, so we'll move on to that. So here also what happens when the alkene is treated with the osmium tetroxide and in presence of a base, and then the diols are formed. Okay, first the osmate ester will be formed, again upon oxidizing upon hydrolysis will end up with the diol formation. First I will show you in the next slide. Same point, instead of 3+2 cycloaddition, 2+2, in this 2+2 cycloaddition, and we have to rearrange it. First one intermediate will be formed. To that intermediate, if we will rearrange it, that osmate ester will be formed. First osma oxetane will be formed, that is your intermediate formation, and then if we will rearrange that for the formation of an osmate ester purpose. Okay, and then that will yield you the diol formation. And so recent studies, what they have said is this can be operative with both the mechanism. It can be either from the 3+2 addition or 2+2 addition, cycloaddition. And okay, so it is needed, the reaction condition is needed over here. You have to focus on the reaction condition, then only you will go to the reaction, further reaction. Let's see, so I have named it as a scheme 1 and scheme 2. So in the scheme 1, you will be studying for this 3+2 cycloaddition reaction. So in this 3+2 cycloaddition reaction, you can see here osmium tetroxide, right? So this is your osmium tetroxide. Here if you will see, this is given as a position 1, 2 and then 3, alright. So here in the alkene, 1 and 2. So this bond attacks over here, and then again this bond shifts, and then there is attack of this bond towards this side, second position. So you can see here, this is a 3+2 cycloaddition. Okay, so here from here it will start. First you have to attack towards this side, then towards here, and then this will go over here, resulting you in this intermediate 8, and then this is just like a transition state formation, and after this is you will end up with this osmate ester. Okay, after the formation of an osmate ester upon hydrolysis, what happens here is upon hydrolysis you will result in the trans diols. You are taking the trans alkene, you are ending up with the trans diols. And then here if you will see, again upon addition with the 2+2 cycloaddition reaction, and this is your one position and then 2, right? So here this goes and attacks towards here, and then this will come and bind here. You will end up with the oxetane, osma oxetane. Okay, this upon rearrangement you will end up with the osmate ester, and again upon hydrolysis you will end up with the trans diol formation. It is a cis diol, sorry. This is also cis diol, this is also cis diol. And then moving on to next, this osmium tetroxide is quite expensive. So the conditions will where here we have to enable certain conditions. because it is very expensive. Okay, so here what we are doing is we are taking only 5% of osmium tetroxide is sufficient for oxidizing the alkene. Okay, so this stoichiometric amount has to be maintained when the reaction is taking place under the condition of your NMO. NMO is your N-methyl morpholine N oxide. So this reagent if we will use in presence of osmium tetroxide for the alkene oxidation, and so at that time only 5% of osmium tetroxide is used for the resulting in an diol formation. Okay, so here if we are taking an alkene and if we are treating it with NMO of 1.5 equivalent, and upon treatment with the catalyst osmium tetroxide catalyst under acetone or water, okay, under this condition, so the diols are formed with the regeneration of your osmium tetroxide. Here the condition is you are reoxidizing the osmium tetroxide, okay, in situ. And then if you will see here again you are taking an alkane upon treatment with osmium tetroxide catalyst NMO in the presence of an acetone or water, again resulting in the diols formation. If you will see here, this is your Upjohn's reaction. In the Upjohn's reaction, and the condition you have to remember is the reagents which will vary over here is osmium tetroxide and the co-oxidants. Okay, that is your in presence of barium chlorate or sodium chlorate. So sodium chloride or barium chlorate in presence of hydrogen peroxide. Okay, this is your hydrogen peroxide. In the presence of an hydrogen peroxide, so you are taking a cycloalkene and then if you are treating it with the osmium tetroxide in the presence of titanium dioxide and treatment with the tertiary butyl oxide, tertiary butyl hydrogen peroxide, and you are resulting in it with the diols. And then again same thing if you are taking the cyclohexene, and then if you are treating it with the NaClO4, that is your sodium chlorate or barium chlorate, metal chlorates you have to take. In the aqueous condition you are ending up with the diols. Same thing here, metal changes, silver chlorate. Okay, if you will take in the presence of an aqueous condition, and here this and all is not affecting, you have to see only the alkene has to be focused. Okay, the diol formation will take place. Moving on to next, here you can see the other oxidation. It depends on the reaction condition again. And here this reaction is known as, if this reagent is there like osmium tetroxide with the sodium iodate, okay, sodium iodate, tetraiodate. What happens here is combination of osmium tetroxide and NaIO4. That reagent is known as Limix-Johnson reagent, and so here if you will see the ozonolysis will takes place. Okay, we are taking an alkene, double bond is affecting over here, and osmium tetroxide in the catalytic amount, it will react to the double bond. Okay, and then it will result in the osmium ester which will again then decomposes in the presence of sodium periodate, sodium periodate, and sodium periodate to give the cleavage products as the diols. So in the one you are getting an aldehyde, and in one more you are resulting in the ketone formation, carbonyl compounds you are resulting. So here if this breaks, you are getting the aldehyde, and here you are resulting in the ketone. And in the example, if this R group will vary with the with respect to an alkyl groups. It can be either the CH3 or the benzene and alkyls or an aryl groups. Okay, so if we will take this compound precursor, and then if we will treating it with the osmium tetroxide in the presence of the sodium periodate, it upon treatment with the THF in the aqueous condition, what happens here is this bond when it breaks, so what happens here, you are getting ketone as well as an aldehyde. Okay, here if you will break it, this CHO, CH2 4 times, and then CH3 COCH3, you will end up with that product. Okay, and then moving on to next slide. I didn't thought of doing the mechanism, so I have not shown the mechanism for that reaction. If you want, I will do with the mechanism. Please put a message in the comment box. Reaction of an alkyne. So this is the next application part. At in the alkynes, how the osmium tetroxide gets affected. So here also what happens, hence when an alkyne is treated with the osmium tetroxide in the presence of tertiary amines, okay, then you will end up with the 1,2 diketones. So here if first one intermediate is formed, when an intermediate is formed upon treatment with the Na2SO3 sodium sulfate, which will yield you a 1,2 diketones. Here the non-terminal alkenes will be affected. From the non-terminal alkenes only you are ending up with the product as 1,2 diketones. Okay. So moving on to next, terminal alkenes of an oxidation. So if you will see here, again this gets break up, this bond is getting cleaved out, resulting you in the with this osmium tetroxide upon treatment with the sodium sulfate as the agent. So you are ending up with the hydrolysis. Upon hydrolysis, you are resulting in carboxylic acid with the liberation of the carbon dioxide. Moving on to as a catalyst, how it will react. So as a catalyst, it is very expensive and a toxic reagent, so it is used in very small amounts with the other oxidizing agent. Okay, so we are taking the other oxidizing agents such as hydrogen peroxide and all. Also with that, if we will do, we are taking very small amount. We in this reaction, if I will speak, so first reaction, if you will see, we are taking an acraldehyde. I mean, an acraldehyde is treated with the hydrogen peroxide, and upon treatment with the osmium tetroxide, what happens here is this bond, when it's break, at that time it will hydrolyze to give you OH, and here also a OH conversion, alkene to an OH conversion, and so you are getting the glyceraldehyde as your end product, final product. And then again, if you are taking the benzene as your starting material in the presence of hydrogen peroxide upon treatment with the osmium tetroxide in tertiary butanol, well, at that time what happens, again the mesotartaric acid is formed. Okay, upon several conditions, upon several hours. Conjugated double bonds are also, this double bonds, if you will see, that will also be hydroxylated in presence of osmium tetroxide and hydrogen peroxide. So if you will see here, again you can understand like this alkene is getting affected by the formation of an OH. You are ending up with the alls formation. Okay, so if you will speak about this reaction, and this starting material, you are ending up with the product of alpha beta dihydroxy ketones. If you will take the cinnamic acid, and then upon treatment with the same reagent, hydrogen peroxide or osmium tetroxide, and what happens here is, again this gets affected, OH and then OH formation, so you will end up with this product. Okay, and then moving on to third reaction, if you will see, if you are taking this acid and then if you are treating it with the NaCl sodium chlorate and sodium perchlorate, and then upon treatment with the osmium tetroxide 50 degrees Celsius, you are maintaining it for 1 day, 24 hours, so you are ending up with the product as mesotartaric acid. Okay, thank you. If you have any doubts, you can ask me in the comment box. If you want any of the mechanism like which I have shown for that beginning reactions in the previous slide, please do ask in the comment box. Thank you.